Hi, I'm Jun-Kai from National Taiwan University. I'm going to present our work minimizing quantum Rényi divergences via mirror descent with Polyak step size. This is the joint work with Hao-Chung and Yen-Huan, and the paper is available on arXiv. Our main contributions are twofold. In theory, the proposed method is the first guarantee to converge extension of the Polyak step size to mirror descent. And the numerical results show that entropy mirror descent with the Polyak step size converges fast for minimizing quantum Rényi divergences. In this work, we consider the four information theoretic quantities, which are called Pez-Augustin information, sandwich-Augustin information, conditional sandwich Rényi entropy, and sandwich Rényi information. To be more clear, optimizing these quantum Rényi divergences occurs in various tasks. For example, the quantum Augustin and the Rényi information characterize the area exponents in channel coding, and quantum conditional Rényi entropies can be used to bound the convergence rate of privacy amplification and analyze the security of quantum key distributions. However, solving these optimization problems is a non-trivial task. There are three main challenges. The first one is that they lack closed form expressions due to the non-commutative nature. And the second challenge is that if we use projective gradient descent to optimize these problems, the algorithm might not well defined because projection onto the set of quantum states might cause a low rank density matrix, which causes the corresponding derivative might not exist. This is also called the stalling issue. And the last one is that we show the boundary gradient and boundary Hessian conditions do not hold for Rényi divergences. Therefore, the standard entropy mirror descent lacks a convergence guarantee for these problems. Because of these challenges, we consider the following general convex optimization problem where the constraint set is closed and convex in a finite dimensional norm space, and the objective function is only required to be convex and differentiable. We assume that there exists a minimizer and the minimum value is finite. And our proposed method is mirror descent with the Polyak step size. Mirror descent is expressed in equation 1, where dH is called the Bridgman divergence induced by some convex differentiable function h. When h is chosen as the negative von Neumann entropy, it is called the entropy mirror descent. For Polyak step size, we want to reach a target level delta ft that is smaller by some scalar delta t over the best value achieved so far. Both mirror descent and the Polyak step size with the two norm are already known, whereas the combination of the two is novel. Our method is guaranteed to yield a delta optimal convergence guarantee with delta positive and arbitrarily small. Moreover, it is easily checked that our convergence guarantee applies to quantum Rényi divergences. Finally, we report our numerical results of computing the four information theoretic quantities, which were introduced in previous slides. Our method is compared with mirror descent with the armyhole line search, which is the only algorithm we know that provably converges for the four quantities. From the numerical results, our method is competitive in terms of the elapsed time. So in terms of the number of iterations, it seems to be slower for computing the conditional sandwich Rényi entropy and the sandwich Rényi information. The reason is that in each iteration, armyhole line search requires evaluating the function value several times, which introduces additional computational burden. This is a brief introduction to our work. Further details can be found in the paper. Thanks for listening.